Hello and welcome. In this tech report, I'll discuss police lidar. At its core, police lidar is just like any other lidar, sends a laser beam towards some target. The part of this beam gets reflected toward and sent back toward the sender or the police lidar, and the receiving portion of the police lidar calculates the time it took the light impulse or laser beam impulse to fly to the target and back. Meaning the method used is something that's often referred to as time of flight calculation or time of flight method. All lidars pretty much work the same. They send a short impulse of energy of laser light toward the target and calculate the time it took to for that impulse to be returned. The calculation is quite simple. It essentially means multiplying the speed of light, which is constant. That's speed of light for vacuum, and in the air it's pretty much the same, a very small difference. So the speed of light is multiplied by the time it took for that impulse, laser beam impulse, to fly toward the target and back, and divided by 2. Divided by 2 because we want to calculate the distance from the laser beam sender to the target, and the time that essentially reflects the time it took for the beam to go there and back. Therefore, we divided by 2. At its core, the method is extremely precise because measuring the time with today's electronics is not a problem. So for if we are talking about a distance of 100 meters, the time is 0.65 microseconds. That type of time is very easy to be measured with today's computers. Even it might have been a slight problem when the computers were running at frequencies of megahertz. Today they run at frequencies of gigahertz. So measuring the time of 0.65 microseconds is a very simple problem. And the constant, the speed of light, is obviously very well known. So at its core, the distance calculation is extremely precise. All the problems and challenges regarding LiDAR come from the fact that well, we have to make sure that we know what distance we have measured. So if we are trying to measure the speed, to get the speed, we have to measure some distances, at least 2 distances, at some time interval, and we'll make sure that those 2 distances are from the same object. If we measure one distance from a car and another car from some road sign or a motorcycle, that's not gonna be the speed of the car. Sometimes there are misconceptions about how LiDAR works. Some people think, and for example, that graphic seems to somehow suggest that LiDAR requires a mirror-like reflection. That's not the point. That's not how this works. LiDAR works pretty much the same way as a situation when we would point a flashlight at some object. So the light from the flashlight or that laser beam from a LiDAR gets sent towards some target. Some of that energy of light will get absorbed, and some of them will get reflected back. And it's not gonna be, and for most objects there are not perfect mirrors. Most of the energy will essentially be scattered in various directions, and some of that scattered energy will be sent back or be received by the LiDAR receiver, and that's how we measure the distance. And just like with the flashlight, there are similar issues concerning, say, the type of the surface we are reflecting the laser beam from. If the surface is perfectly white, then all of that energy will get scattered and sent away from the object. If the object is perfectly black, then all of the energy will be absorbed. And for that reason, there's some products being sold, like, say, a laser or LiDAR bra that limit the ability of the LiDAR to read vehicles from larger distances. But for this to work at all, that bra will just have to be like perfectly black and not covered with dust. Anytime there's dust on something like this, then obviously that doesn't work anymore. So these things are being sold, but I don't think they are especially effective. Police lidars, or laser-based speed measuring devices that are commonly used by police today, they have very specific construction. What they do, they use a relatively wide beam, typically from 2 to 2.5 milliradians. Generally, in other applications, that beam is much narrower. For such small values of angles given in milliradians, it's actually very easy to calculate or understand, because 2 milliradians means that the beam is 2 millimeters in diameter at distance of 1 meter, or 2 meters at diameter at the distance of 1,000 meters. Very easy to imagine or kind of calculate in one's mind. For that reason, I'll refer to that construction as the cone beam LiDAR. The reason for stressing is because there are newer devices, newer speed measuring devices that use laser beams and or LiDAR, and I'll briefly describe that too. The reason that other type of construction of a LiDAR should be mentioned is because people, not only because such devices appear for use by the police, but because that other construction, which I'll call the scanning LiDAR, is a much more common use of the laser or LiDAR technology. What this is about is we again still have the same basic construction, meaning some sort of a laser beam transmitter that sends an impulse of light or laser energy and waits for it to be returned. But in addition to what was shown before, there is also a rotating mirror or a prism that allows that beam to scan horizontally and sometimes also vertically. And there are lots and lots of application of that type of LiDAR, which I'll call the scanning LiDAR. And for people who might understand the scanning LiDAR or scanning LiDAR applications, and then looking at police LiDAR, they might think that the police LiDAR, including the cone beam LiDAR, is doing the same. Well, it's not, and there are some big differences. And obviously, in this kind of application, generally, it does not make sense to make a beam larger. It makes more sense to get that beam as narrow as possible, because that allows if these impulses are fast enough, it allows to have much bigger resolution. So if we are using this application for, say, scanning some objects, then that scan becomes much more precise the narrower the beam is. And that type of a LiDAR is used for a lot of things, for building 3D models of, say, sculptures or different objects or terrain or clouds, things like that. I'll probably make a separate tech report discussing the scanning lidars, including the scanning lidars that were specifically built to be used as handheld or moving devices for measuring vehicle speeds and speeds of many vehicles in traffic. They are very interesting devices. They also have some weaknesses, and this is why that will be very interesting. In this report, however, I'll concentrate on the cone beam lidar, or the lidar that is most commonly used by police today. So the most important issue to explain is the reason why that laser beam is widened to the 2 or 2.5 milliradians. What advantages it gives and what problems it creates. So the core problem of using LiDAR for measuring speed of some moving object is that we need distances of the same element of some vehicle or some object at two different time moments. If we don't get distance from the same element, then obviously that's not going to be speed of the device. If there is some error, meaning that the distance is not from the first distance is from one object and another distance from another object, and obviously the speed is completely wrong. However, there is also a problem if that one distance is from one part of the car and the other distance is from some different part of the car. That also will create a problem. That also will create a wrong speed measurement depending on what time period we used between these two impulses, between two distance measurements. In order to understand details of construction of police LiDAR and the challenges that occur there, let's imagine we are trying to build a police LiDAR that only uses two distance measurements in order to determine speed of some moving object. The maximum allowed error for speed measuring devices used by the police is about 3%, and that is just total error of the entire device, all the circuitry and everything like this. So the error introduced by just the method selected by itself, let's assume we have to be within 2% range, and that's will allow us to explain the construction details. So let's suppose we are measuring a car or other vehicle traveling at a speed of 100 kilometers per hour. That means that in 1 second that car covers approximately 28 meters distance. So in order to measure its speed with 2% maximum error, the maximum distance error between these two distance measurements is 56 centimeters. If now we are trying to measure the speed using 0.1 second intervals, that means that the maximum then the car travels 2.8 meters in that time, which means the maximum allowed error of the distance measurement is 56 millimeters. If now the time interval between those two distance measurements is 10 milliseconds, then the maximum error will be 5.6 millimeters. If now the period is 1 millisecond, then the maximum allowed distance error will be 0.56 millimeters. And that already shows the problem, because you have to measure two different distances at some time interval, and now you have to hit the same point on the vehicle. Even if that lidar was not held in someone's hand, meaning there was no danger of the operator moving it a little bit left or right or up and down, then the movement of the car already would shift the point. If the beam was narrow, the movement of the car would already produce an error, because the beam being pointed at one point on the mask of the car, after the car moved, it would be on a different part of the car. So if now this time interval was short, say 10 milliseconds, then even that would already create a very, very large error, because that movement on the car would be much larger than the allowable error. I suppose it would be possible to design a lidar that would operate in a fashion where the operator would be required to make one precise shot at some vehicle, or to measure one distance, and then wait, say, a second, and try to hit the same point on the same vehicle. Then the problem of that error wouldn't be that large, because he would have to make a mistake of more, somehow hit something that would be 56 centimeters further to get that error to be too large. But that's not the method that they chose, because I guess when the lidar was designed, the issue was how to verify that, how to automate this whole process, how to make sure that the operator actually hit the same point at two different time measurements. So I suppose for those reasons they chose a slightly different method, or completely different method, depending on point of view. For better or for worse, they chose a strategy to create a lidar that will produce a speed measurement at a time of 1/3 of a second. That's the typical thing for commonly used police lidars. So 1/3 of a second means that our error produced by not precise aiming of the laser, the maximum error allowed is 90. It has to be less than 19 centimeters, and that is already a little bit of a problem, because it's very easy to move a laser beam on the car, even on the same car, and have that error larger than 18 centimeters, just sliding it on the mask or something like that. And that, I think, is the first reason why they chose to use this cone beam that has a fairly large diameter, because when that beam is pointed at a vehicle and you read all the elements within that beam on a single point from a very narrow beam, then that allows averaging just of each single distance measurement. If the beam was very narrow, then we performed one distance measurement and at one point in time, and then another distance measurement a second moment in time, and that second one was moved on the mask of the car. Then the signal received by the lidar would be essentially 2 bars, and that error would be seen there. Now, on the other hand, if the beam of the lidar is wider, like shown on that picture, then this movement of the point between the two distance measurements would result in a completely different effect. Because if the beam is wide, then you are not getting a bar as the return signal. You are getting this impulse spread in time, and a slight movement along the shape of the car will mean that you still will be getting a lot of energy from the similar to the previous position. So if you compare these two signals, and now if you kind of if that circuit is set up so the computer processes this the signal just by cutting that return values in half, then you might actually be getting the same distance measurement from both of those things. So widening the beam averaged the reading. That's the whole point. Or to look at it a different way, moving it a little bit along the mask still means that most of the energy is reflected from the common area of those two measurements, and not a completely different distance measurement. The construction of police lidar as commonly used today was first introduced by company Laser Technology Incorporated from Colorado in the United States. They filed a patent in 1992, and already then they were introducing that lidar to be used by the police. That patent describes the second important element of the strategy being used. The first being the widening of the beam, the second being that there isn't 2 or 3 or 4 distance measurements being made, but minimum 60 distance measurements are required by their lidars to begin with, performed within 1/3 of the second to produce a single speed measurement. So there is about a minimum 60 measurements in 1/3 of the second. That means a separate distance measurement every 5.5 milliseconds. Now that's the minimum. The lidars actually sometimes they take longer time. If those measurements are unstable, the lidar produces like low-pitched growling sound, letting the operator know that it is reading unstable or incoherent distances, and then it takes longer. But 1/3 of a second is the minimum time required to produce a single speed measurement. And now the question is, what do they do with those 60 distance measurements? They are all fed into a special statistical formula or algorithm called least squares algorithm, and basically that produces a single speed measurement out of all of the data. That formula is shown in the patent. There are some typographical errors in it, but they corrected it later. This least squares algorithm is described in any math handbook and statistics handbook. You can look it up on Wikipedia. It's a very commonly used algorithm, and it makes perfect sense. The problems that occur with that lidar is not the statistical processing itself, but some other issues which I'll describe later. To describe it in simple terms, this whole algorithm of least squares in simple terms is that the device collects these 60 measurements of distances measured at different time intervals, and then creates like a chart of all those points, and those points are scattered because of the errors produced by movement of the say shaking hands of the operator, or the movement of the vehicle being measured, the beam hitting different point on the mask. So anyway, so there is 60 different distances at different time periods, and what this algorithm does, it is pretty much tries to calculate a straight line that is near the nearest of all of those points, and the slope of that line gives you the speed, the average speed within this whole package of data. That's what this is about. To understand all the effects that take place when this method of the police lidar is used, when a lidar is being used to measure speed of moving vehicles in various situations, you have to picture how the lidar beam looks like compared to a shape or a front of the outline of an average car. It shouldn't be a surprise that measuring speed or using a lidar like this from a distance, say 2 to 100 meters, 200 meters, is not a problem, because first of all, that that beam is very small compared to size of the vehicle, so it's not that easy to make a mistake and move that beam beyond the car. First, because the car is so near, and second, because the beam is so narrow now. But if you look at the using that method at a distance of say 600 meters or 700 meters, then you can see that already not precise targeting of the vehicle will result in that beam hitting beyond the vehicle, not at the vehicle but outside of it, and that's the problem, and that's what I was able to determine, and that's what a lot of other tests were able to determine. Obviously, the problem is smaller if the target vehicle is larger, if it is at front of a truck or front of a bus. Well, because again, the beam is the same size, but the target is larger. So again, from the same problems that occur for a car from the distance at a distance of say 700 meters, they occur for a truck at a distance on at 1000 meters. For a motorcycle, it goes, of course, the other way. Already, using this ultralight LTI 2020, trying to measure a motorcycle at a distance of, say, 200 meters, then it's very, very easy to, just by unintended movement of the operator's hand, something like this, to go beyond the motorcycle. So it is very hard to maintain that beam on the target at such circumstances. So the whole problem that occurs is what happens if the operator tries to measure a motorcycle or a car, but some of that beam or most of that beam does not hit the motorcycle or the car, but flies past it. Now, if this is measured, being done on a perfectly straight road, and there is nothing behind, then that beam, the laser beam, will just fly far into the distance and will never return. But now what happens if that beam hits something, if there is say a wall behind, or some sort of a hill or something like this, and that signal gets returned? Well, the problem is, in some circumstances, that gets included into the calculation. that gets thrown into the statistical bucket of those different measurements and averaged out. Theoretically, the device shouldn't be doing it. There should be some methods to determine which of those distance readings are valid and which are not. But as my tests have shown, that not always works. A very common situation that creates problems is when the operator is standing at the bottom of some hill and tries to measure a vehicle that's traveling down that hill. So he has to follow that vehicle for at least 1/3 of a second. Otherwise, the beam goes beyond the vehicle, or it slides along the vehicle, and that creates, now if he doesn't hit that vehicle and the beam goes beyond it, part of the beam reads the distance from the road. And why is that a problem? Well, because if he has to slightly rotate or move that lidar to follow the vehicle in order to keep targeting it, the distance being received from or measured from the road, it also changes. So if you look at that drawing, you have to follow the vehicle to make a measurement. But now if there was no vehicle there at all and you perform the same movements, then you will also be receiving varying distances. And these varying distances will go into that formula and they'll produce speed calculation. In this particular situation, that will actually be that speed will be larger than the vehicle, so than the vehicle speed. So if you if say the lidar was not calibrated correctly and the beam was hitting on the side of the vehicle, and the operator still followed the vehicle or thought he was following the vehicle, and the targeting optic was not set correctly, he will be receiving much larger speed. That can be easily proven by simply using a lidar on an empty road and just performing those movements, just like following an imaginary vehicle that isn't there, and you will be able to get speeds. I was able to do it consistently in many circumstances, and that's the problem. See, the second problem is that if the operator is not correctly trained in how the lidar works, when he is performing such measurements from large distances, then naturally if the beam is large, then he'll be getting the situations often where some of the beam hits the car and some of the beam hits the road before or after the car. And those situations, those distances being inconsistent, a lidar will often produce that low-pitched growling sound. And if the operator doesn't know what he's doing, he will try to get rid of that lidar growling, or fix that problem of the lidar complaining by targeting slightly below the vehicle or above the vehicle. And what that will do, it will produce speed readings that have absolutely nothing to do with the speed of the vehicle. That issue was hard to deal with when the lidars being used did not have cameras, because dishonest or incompetent operator could produce such errors and nobody would be able, there would be no means to verify what he was doing. Now, with lidars like such as TrueCam being equipped with cameras, you can easily verify all that. And that's what I was able to do, and I was able to research that sub-issue quite extensively. All those weaknesses of LiDAR were actually discovered in the United States very early on. Well, just several months or just 2 years or so after this device was being introduced and used by the police in the United States. There were many complaints about it, and lots of people contested the charges, went to court, and in the state of New Jersey, many such cases were grouped together into a single case, and the court did a really good job in trying to determine what was the problem. They called the designers of the device to testify, and well, the first question was exactly how they determined that this device gives reliable readings from large distances. And the designers or the representatives of the company that produced the device, the Laser Technology Incorporated, they testified that they simply placed like large mirrors on trucks, and that's how they were able to obtain these measurements at the distances of 3,000 feet or so. And when judge heard that, he obviously decided that this absolutely was not a valid test, not a valid proof of concept, not a valid test of reliability, and he issued an order prohibiting the use of those devices. As the result of that order, the police of the state of New Jersey, they tried to somehow salvage the situation, figure out what is going on, and they performed thousands of tests. It took 18 months, and during that time they tested and documented 1,908 cases of different situations, different uses of that LiDAR for measuring speeds, and they produced the results to the court. Now, what has to be mentioned is, as far as I was able to determine, it wasn't really scientists or engineers that supervised the test, but it was just lots and lots of empirical tests that were done by the police. Maybe there were some experts who were supervising. Nevertheless, the whole point was that the result of those tests, they found that device was reliable when it's being used up to 1,000 feet or 305 meters, and that's what the judge ruled on. And so he ruled that only their measurements using this device at the distances of up to 1,000 feet or 305 meters are admissible as evidence. And if there are measurements or readings obtained in excess of that 1,000 feet, they can only be admitted if there is some supporting evidence and expert testimony. And the additional issue is that in the United States, they developed additional procedures that help eliminate errors. And what they call it is, they call this full tracking history. What this is about is the operator does not perform a single speed measurement. He tries to perform several of them. Therefore, from what I was able to determine, if someone uses those devices the same way as the United States Police uses them, meaning they never performed measurements in excess 300 meters or 1,000 feet, and they also do this full tracking history, meaning they start measuring at, say, 250 meters, then they make another measurement at 200 meters, then 150 meters, 100 meters or below, there is very little chance of producing an erroneous reading, even if the lidar is not equipped with the camera. Well, and that's where the problem occurs, because in some other jurisdictions or outside of the United States, that precedent or these rules are not being used because it's different jurisdiction. And according to the manual, or interpretation of the manual, a lot of people assume that you can actually use those devices reliably to make speed measurements, not just single distance measurements, up to 1,200 meters. And that's simply not true. There are many problems that can be clearly seen by examining evidence from, say, the recordings of TrueCam devices nowadays, which I was able to do. Now, one would think that a LiDAR is supposed to detect these situations where a beam partially falls on the vehicle and partially outside of it. And the manual suggests that it sometimes is doing it. For example, when the lidar growls because it issues this low-pitched sound, indicating that it's getting inconsistent distance readings. Again, it works sometimes, but in some cases it doesn't. I was also able to determine that in the United States, people try to obtain the exact details of that algorithm that tries to validate the data. And the companies consider this trade secret, and they never released it in full, as far as I was able to determine. The only details that are published in US literature is that there is a requirement that 80% of the transmitted energy must be received. That's one of those rules. Now, that doesn't really make much sense, because depending on, for example, on a color of the target, there is much less energy being returned when the target is white and when the target is black. What they likely mean by it is that 60% of the energy of that impulse received must correspond to a single distance. Now that to me makes sense, because if, for example, we get 60% of that impulse says the distance is 100 meters, and 40% of that impulse says the distance is 200 meters, then, well, you should look at that 60%. And makes sense. Now, if there is a bigger difference between those, then you shouldn't be reading any of those. That whole distance measurement should be rejected. That makes sense to me. The second rule that's reported by the US literature is that 90% of the returned signals, meaning probably just all those distances, different distances, like 60 out of 60 of them or so, must be within plus minus 1 mile per hour or 1.6 kilometer per hour, based on that algorithm or average of the least square statistical method. Again, that makes sense. Okay, so if we are trying to draw that line that represents the speed, and we have points that are way outside of that line, then we can reject those points and then try to get more. Okay, so that again makes sense. But there are situations which I was able to document where that algorithm is not able to detect obviously erroneous measurement, where the operator starts measuring by pointing the lidar on a hill, a grassy hill near the road, and then slides it along the road and then ends up on the motorcycle, and the lidar is not detecting this as an erroneous reading. And so that's the kind of problems I'm talking about. I did this research because in some other jurisdictions, specifically in Poland, that device is being used as they try using it to distances up to 1,000 meters and more. And the drivers are used as guinea pigs of sort, and that's why they asked me to diagnose that problem, partially because they wanted to know what is going on, and secondly there was an interest in perhaps developing a lidar here in Poland. At the end, all that work which I own was not utilized because they changed their mind. But nevertheless, I owned all of this, and there is a lot of data, a lot of interesting conclusions, a lot of say ideas of how to improve that device. If there is someone interested in that research, I might be I will be willing to share it, especially if someone is developing a better lidar. I mean, that's what this should be about. Okay, as I said, I mean, I have absolutely no problem with that device being used the same way, the way the precedent or court that's dictate it being used by U.S. law. Okay, but I have big problems with someone saying, well, it can be used reliably to measure, say, a motorcycle from 700 meters. There are lots of problems with it. That's what the issue is. Now, a few words about what makes me qualified to make such research or make such reports. I worked for many years in the United States as an electronics and engineer and a programmer. I was building and designing test equipment for various US companies. Equipment that I designed was used by Toyota, Isuzu, many other companies. My last project in the United States was writing software that is being used for pretty much all car racers in the United States, outside the companies that they make their own software other than buy the products available for everyone. You can see my software on TV in the United States from when they show races, car races, drag racing or circuit track. So that's all. The software that's being used is mostly written by me. This is why I was able to do all this work, and as I said, I will be interested in utilizing it further. So if someone is interested, please let me know in comments. If someone is interested in me making more reports on various technical devices or all the problems that occur with them, please also like the video, comment and subscribe. And that would be all in this tech report. Thank you.